Okay, this is section 3.4, part 2. This is the second derivative test. This is a test for whether we have a relative max or relative min. So just a reminder, the first derivative test is the one that we've been using up until now. So if we have a critical point, so that'd be when the derivative is equal to 0 or does not exist. If the derivative goes from positive to negative, that means we have a relative max at that point. If our derivative goes from negative to positive, that means we have a min at that point. This is another way to determine that where we don't need intervals. The nice thing about this particular test is we can use information from a single point to determine whether we have a relative max or min. Now, first of all, this only works if our critical point is specifically coming from our derivative equals 0. If you have a, fix this. This is not correct. Can't use this test if you're getting your critical point from f prime of a not existing. So if f prime of a does not exist, your only option is the first derivative test. So this only works if f prime of a equals 0 is how we're getting our critical point. Okay, so basically it's pretty simple. You take the critical point, instead of doing a number line, you take that critical point and plug it directly into your double derivative. If your double derivative is positive, now think about what that means, as we talked about in the other video. If your double derivative is positive, it means we're concave up. When we put that in connection with a horizontal tangent or a critical point, what that's indicating is we're concave up with this 0, so that guarantees that then I will have a minimum. So I just take that value, plug it directly into our double derivative. If it's positive, that means we're going to have a minimum. Conversely, if we take that critical point, plug it into our double derivative, and we get something less than 0, well, now that means I'm concave down with that horizontal tangent, which means that that is a relative maximum at x equals a. And then once again, if I plug my a into my double derivative and I get a 0, well, that means that this test is inconclusive, and once again, I would have to go to the first derivative test. Okay. So once again, we can only use a double derivative test if it's our critical point specifically is coming from f prime of a equals 0. If it comes from D and E, we have to use the first derivative test. And finally, if we get the double derivative is equal to 0, then once again we have to go to the first derivative test. Okay, so let's look at a couple examples here. Okay, so let's do our first example. So once again, we're using the second derivative test to identify relative extrema, either relative max or min. We start with polynomials, and once again, polynomials are well behaved. We don't have to worry about continuity issues. We don't have to worry about differentiability issues. So when I'm determining relative max and mins, the first thing I always do, it doesn't matter what test I'm using, I want to identify critical points. So critical points are going to be when my derivative is equal to 0. So this will be 8x to the third minus 32x. We want to know when that's equal to 0, or possibly dne. Let's go ahead and factor out an 8x here, which will leave me with x squared minus 4 equals 0. So I get 8x, x plus 2, x minus 2 equals 0. So we have 3 critical points here. Okay. Once again, the double derivative test only works when our derivative equals 0. It does not work if our derivative does not exist. If that's the case, then we have to do the number line first derivative test. All right. So what's nice about this is we don't have to do a number line. All we do is we take our double derivative here. So our double derivative, so that's 24x squared minus 32. Now all I'm doing is I'm taking these values and plugging it directly into our double derivative. So our double derivative, we just plug it directly into it. So our double derivative, if we plug 0 into this, we get 0 minus 32, so that's negative 32. That's less than 0. So if I'm less than 0, that means I'm concave down. So this means, so we have a relative max at x equals 0. And that's all the justification I need. The identify as a critical point with showing the double derivative is less than 0 is all I need. So that's my first one. Now we're going to take -2 and plug it in. And actually, let me just point out, -2 and 2, they're either both going to be a relative max or both a relative min, because they're both going to do the same thing. So I'm just going to treat them both as just one value, because it doesn't matter what I plug in there, negative or positive. That's going to be 4. 4 times 24, what is that, 96? 96 minus 32. So that is, get that right, because that's 48, yeah. So that's going to be 64, which is greater than 0, okay? So we have a relative min at both x equals -2 and x equals 2. And that is it. That's our double derivative test. Okay. Let's do one more example, and that will be it for the double derivative test. Okay, so this will be our second and final example for today. Same thing, we're going to use the double derivative test to determine whether we have relative max and mins at our critical points. In this case, we have a function that once again is not a polynomial, but it is well behaved. As I've talked about, e to the x doesn't cause us any domain issues or differentiability issues, so we're going to be good here, okay? So let's go ahead and start with our critical points. So, no, let's not use that. Take the derivative. Now notice we do have product, and we do have to do chain rule as well, because it's not just x there, it's negative x. So the derivative of x is 1, copy down e to the negative x, plus, copy down the x, the derivative of e to the blob is e to the blob, but then don't forget to take the derivative of the blob. The derivative of negative x is -1. Now, just for simplicity, we know that -1 is just going to change this plus to a minus, so let's go ahead and just do that there. Okay, so that is my derivative. I'm interested in when that's equal 0. So, you know, don't be thrown off by this. I'm just going to factor out this e to the negative x, which will leave me with 1 minus x equals 0. Okay, the e to the negative x is never going to be 0, so we're not going to get any critical points from that. So all we're left with is a 1 minus x equals 0, so x is equal to 1 is our only critical point. So now from here, I got to find my double derivative. So here's my first derivative. If this wasn't already simplified, I would want to simplify this. So let's take our double derivative here. We got to take the derivative e to the negative x. Got to use chain rule. So the derivative e to the blob is e to the blob. The derivative of negative x is -1. I would say with this minus, be careful here, because we do have to do product rule. So we'll deal with simplifying later. So let's just focus on this part. Let's take the derivative of that. Derivative of x is 1, copy down e to the negative x, plus copy down the x, the derivative of e to the blob will be e to the blob, and then take the derivative of the blob will be -1, and then once again, that -1 is just going to change that to a minus. Okay, let's do a little simplifying, because I do have to work with this. One of the trends hopefully you're picking up on in this class, you know, simplification isn't a big deal. We do want to simplify when it's going to help us to do the problem, which is what we're going to see in this case. So I'm going to get f double prime of x. This will be negative. So let's go ahead and just distribute this negative using our eraser. So this will give us a negative here, and it will give us a positive here. Okay. And these negative exponents, e to the negative x, I want to move those to the denominator, all right? So first of all, notice these are like terms. So I'm going to call this -2 e to the negative x, and then I'm going to move the e to the negative x to the denominator, making it e to the x, plus x over e to the x, okay? So if you need to put a step in there, go for it, but I think this is going to be the easiest thing to use. Okay, so now I'm going to take this double derivative, I'm going to plug in 1 into it. I get -2 over e to the first. By the way, e is roughly 2.718 plus, and now it'll be 1 over e. So, and actually we don't even need to know that here, because what I'm going to get here, all I have to know is that the fact is positive. I get -1 over e, right, because I have a common denominator. So I get -2 plus 1 is +1. -1. So this will be -1 over e. So this is less than 0. I don't need to know exactly what that value is to know that that's less than 0, which means that if it's less than 0, it's concave down, that means it's going to be a max. So we have a relative max at x equals 1, and we are done. So that's a double derivative test. Yep, that's about it.